Okay, so here's a problem that we want to try to start working with. Hang on a second. There we go. So let's use the conjugate beam method for this problem. So what's the first thing we need to know? Well, what's the first step in conjugate beam is we need the moment diagram. So let's find the moment diagram for this guy. To do that, we're going to need to find some reactions. So let's start. I don't usually like to do it this way, but I will anyway to save some paper. I'm going to assume that I've got shear at A and moment at A. And let's find those reactions. So using right-hand rule, I'm going to sum the moments at A. Make sure they're in equilibrium. So let's sum the moments at A. What do we have? Well, we have the actual moment that I'm looking for, which in my sign convention would be negative. And then there's only one load on the whole system, this 5 kip force at a distance of 15 feet away, and that also creates negative moment. So 5 kips times 15 feet. So it looks like the moment at A is negative 75 kip feet. That seem okay? Mm-hmm. So let's then go ahead and sum the forces in the y direction. We'll assume up is positive. So I have my shear force is up and the 5 kip load is down. So it looks like the shear at A is 5 kips. So what's the moment look like? Well, if I kind of draw a template for my shear moment diagram, we'll start off with, got kind of a wavy line, sorry about that. We'll start off with my shear diagram with the units of kips. So what's the shear at A? It's 5. Everybody see that? So that means we're going to start here at 5. And remember, the change in shear is equal to the area under the load diagram. And what's the area in the load diagram from 0 to 15? Nothing. So there's no change. So we stay at 5 kips. And we also know that the slope of the shear diagram is equal to the load. And what's the value of the load here? 0, so I have 0 slope. So I have a constant shear of 5 kips over the first 15 feet. Now I'll draw positive x and positive axes for my moment. Now what's the bending moment at A? We saw for that it was negative 75. Right? And we also know that the change in moment is equal to the area under the shear diagram. So over these first 15 feet, what's the area under our shear diagram? Well, it looks like 5 times 15, it's a rectangle, that's positive 75. So if I start at negative 75, I end up at 0. And the shape, or the slope of the moment diagram, is equal to the shear. And our shear is constant, positive, and equal to 5. So we have a constant positive slope. So there's our moment diagram. Again, that would be you'd be very happy if you got that on the exam as a shear moment diagram problem. But unfortunately for us, that's about a third of the way through this problem. So, what do we do next? we need to do the conjugate beam. So I'm going to try to get this all on one piece of paper, so let me kind of box this off. And then I'll start over here and let's draw the conjugate beam. Okay, so when we draw our conjugate beam, we map the real connections into the conjugate beam. So a fixed connection in the real beam maps to what in the conjugate beam? A free. And the free end maps to a fixed end. So our conjugate beam then ends up looking like this. Everybody see that? Now, what do we apply as load to the conjugate beam? Well, the M over EI diagram. And M is negative, so we're going to apply it as a negative load. Negative load is down. So we're going to have a load that looks something like this. And that will have a value of 75 kip feet divided by EI. And that'll be over 15 feet, and this will be 15 feet. Everybody see that? So, the problem asked is, what's the slope and displacement at point B? Well, point B is the free end. So to find the slope and we need to find now the shear and moment at B in the conjugate beam. Now the shear and moment at this point is simply just the reactions. So I'm going to come down here and I'm going to assume positive direction for the moment at B and positive shear for the moment. For the shear at B. I just need to solve for those two things. So you can probably see one way to easily handle this would be to convert this into a concentrated equivalent force. Right? I'll just write it. I'll say it's just F1. So what is F1? F1 would be 1/2 the base, which is 15, times the height, which is 75 kip feet over EI. Can somebody calculate that for me? And while they're doing that, we'll go ahead and find this distance. So what's the distance? What's this distance right here? Well, we know in a triangle that the centroid is 2/3 from the small end, so 2/3 of 15 is 10 feet, and then of course all the way over to this side would be an additional 15. So somebody get that value?
Yes.
What is it?
Oh, not that bad. Sorry.
I say it's 450, I'm guessing. 562 point. So 562.5 kip feet squared over EI. Okay, so I have everything I need, right? So let's sum the moments first. So using right-hand rule, I'm going to sum the moments at B and set it equal to 0. So using right-hand rule, my actual reaction moment is positive, and then my concentrated equivalent force is also creating positive. So I'll have plus the actual force, 562.5 kip feet squared over EI, that's the force, times the moment arm, which we've already computed as 25 feet. So don't forget, this is the force F1 and that's that distance. So what is the moment at B? Looks like it's negative, and whatever that times 25 is. What'd you get, Miss Wiseman?
42.
42? I don't think it's 42. 562.5 times 25? 14,062.5? And that would be kip feet cubed over EI. And it's negative. So that means the displacement in the real beam is negative. Does that make sense? That B would go down?
Yep.
I think so. So let's actually compute the value. So we know that the moment in B really maps to the displacement in B, and that would equal negative 14,062.5 kip feet cubed. Okay, let's divide that by E, which is 30,000 kips per inch squared, and then 800 inches to the fourth. And then we're going to come along and say that there's 1728 cubic inches in a cubic foot. Everybody see that? So all the units should cancel out, and we should get what? Close to 1 inch, I'm guessing. Actually, a little more than 1 inch. What's the answer, Miss Wiseman? Huh? .01 is close enough for me, and that's in inches. 1 inch. What about the slope? Well, we get the slope by summing the forces in the conjugate beam and solving for shear. So let's do that. So I've got the shear force acting down minus my force, which is 562.5 kip feet squared over EI. It looks like the shear in B is also negative, and that's not hard to compute. It's just 562.5 kip feet squared over EI. But we know that the shear in B really maps to the slope at B. So what is that slope? Well, we have to do the calculation again. So it's 562.5 kip feet squared. Again, we're going to divide by E, which is 30,000 kips per inch squared. The moment of inertia of our cross section is 800 inches to the fourth. And now we have to convert to square inches, not cubic inches. So there'll be 144 square inches in a square foot. And if you look at that carefully, you'll see it has no unit. All the units cancel out. I think we get a very, very small number. What is it? 0.00337. Okay, wait, here we go. Hang on a second. 0.003? That's close enough. So that's 0.00 whatever radians. Very small angle, as you can see. Also, you'll notice that it's negative. Is that true? I think so, because if you go back and look at the original problem, you probably expect it to deflect something like this and you can see the displacement is down, and you can also see the slope is negative. So that seems to match pretty well. So that's a very, very doable problem. Now, the advantage is that it was not hard. It relied on your skills of knowing shear and moment diagrams and being able to calculate shear and moment at a point, both skills that you should have. What's the disadvantage? You don't get an equation, right? I just solved for it at a point. So if I wanted to know it at other points, I'd have to redo the problem. So it does have an advantage in that it can give you a value at a point relatively quickly, even for fairly complicated section. The other thing to notice is, if your moment diagram starts to get quadratic or cubic or higher order, then this becomes more challenging. So this works great for point loads, because point loads usually generate triangular moments. Triangular moments are not hard to deal with. So any number of point loads on a system, which could be very challenging to do with direct integration, works out very nice with conjugate beam. So any other questions before we end this one? No? Okay. Turn this off. And goodbye.